Good afternoon. I think it's time to start. So, let's have a short break in the chatter, please. Just a short break. It's not going to take very long. Work from last week, I think. Hope it is. So each of these 4 statements, you were supposed to say whether they're true or false. Okay, so let's go A, B, C, D. A. I'll read A, and you can still think about it here, if you haven't done it at home. Who's done it at home? At least read it. 1 person. Anybody else? 2? Maybe. Maybe more? No? Yeah, let's do it now then. So question A is, if you're doing the ratio test in a pivots test, okay, and there is a tie, which means that 2 of the ratios, you're looking for the least ratio. Do you recall what this is? Okay, so when I decide based on the objective row, there's something of the wrong sign. So this is my pivot column. I'm looking for the pivot row. So what I'm looking for is something positive in this column. And then I'm trying to get, what I'm doing is dividing the values, the right-hand sides, by the values in the pivot column. Okay, and I'm looking for the least ratios. What do I do if 2 of these ratios are the least and are the same? So that's what is meant by a tie in the ratio test. What do I do? Raisa, what do I do? Don't know. I'm sure you know. You've just not been listening. That's the problem, I think. So the question is, I want the answer from you, because I'm sure you know. The question is, if I'm doing these ratio tests while pivoting in the simplex method, and it turns out that the least ratio that I'm looking for is achieved in 2 different rows, what do I do in that situation? Do I have to choose one of them, or can I choose any of them? Is there a particular rule? Tell Raisa, and she's going to tell me.
You select the leftmost column.
Oh no, I've already selected the column.
Oh.
Now I'm doing the ratios to select the row. It's a different situation. Okay. Okay, anybody else? Okay, who understands the question? Who doesn't understand the question? There's not enough votes. Okay, we vote again. The question is understood. Who understands the question? Who doesn't understand the question? Okay, I'll say it again. Pivoting in the simplex method. Who is already lost? No one? So far, so good. Okay, how does the pivoting process work in one pivot step? If it's a maximization problem, what I'm doing is I'm looking for a negative sign in the objective row. Who's already lost? Well, then I don't know what to do. That's probably not my fault, but lost at this point. Okay, now when I find a negative element in the objective row, Danzig's rule, the common rule that we've been using, tells us to select the most negative element in the objective row, but it doesn't really matter as long as the element is negative. We can select it for pivoting. Now, we want to know which row will be the pivot row. Who's still with me? Okay, so for these three people, the way I'm selecting the ratio, the row, is I look at the ratio of values in the val column and values in the pivot column. And I divide them in each row where this element in the pivot column is positive. If it's negative or zero, I don't divide, I just ignore it. But where it's positive, I do the division. Now, among these results of the division, so these ratios, I'm looking for the smallest one, and that will determine where the pivot row is. Okay, so who is with me now? Who's too lazy to raise their hand? Well, of course, nobody will raise their hand, because if they're too lazy, then they're not going to raise their hand. Right, now, what happens when two of these ratios or more are the same? Is there a rule that tells me which one of them to pick? Or can I pick arbitrarily? George?
You should be able to pick either.
Yes. So if there is a tie, choose any of the least ratios. Now this question A asks me, is it then true in this situation that when I do the pivot, I get the next basic feasible solution in at least one of these entries in the valve, there is going to be a zero. Okay, let's do it. Who thinks that there's always a zero? Who thinks that it can happen that there is no zero? Again, not enough votes. So try to persuade, if you've raised your hand, try to persuade at least one neighbor that they should do the thing next time out. You see, I'm too lazy to do actually anything. Okay. 3, 2, 1, go. Who thinks that there will always be a zero? A bit more than before. Who thinks that it can happen that there's not a zero? Oh, that's a bit more than before, but still. Okay, so the answer is that there will always be a zero. And remember that the ratio test that we're doing, its purpose is we're taking the least ratio, because if we don't, then what we're going to get is negative entries in the valve. And the simplex method doesn't like, at least that's what you think for now, doesn't like negative values in that right-hand side column. Okay. So we're trying to avoid negative values in the right-hand side columns, and that's why we're picking the least ratio. Now, if some of these ratios are the same, then The ones that we don't pick are going to have a 0 after the field step. Okay, that's the answer. So A, the answer is B. What's question B? I can't remember. Okay, question B is kind of silly. So question B says that if there is no leaving variable at some pivot step, then the problem has no feasible solution. What does it mean that there's no leaving variable? That means that, now ignore this, when I find my negative entry here, I'm looking for the pivot row. The pivot row is the leaving variable because there's a variable that's in the basis, let's say x7, and that could leave the basis. Okay? So I'm looking for something that's positive, but what I see is negative and 0, and negative and 0, and negative and 0, and nothing, absolutely nothing positive in that column. Does that mean that the problem has no feasible solution? Okay, so who thinks it's true? Who thinks it's false? That's a slight plurality. Okay, yes, correct. This is false because what does it mean? Does it mean anything else? Yeah, which is no exact. Okay, anybody volunteer, ready to volunteer the answer? Yes, Freddie. You,
Doesn't mean you've reached the excellent solution.
it does not, but it's a decent guess. But it does not mean that you've reached the optimal solution. Reaching the optimal solution, the criterion is that there are no negative elements in the objective row. Anybody else have a guess or an answer? Okay, what it actually means is that the problem is unbounded, which is to say that there is no optimal solution because you can reach arbitrarily good, large, in the case of maximization, objective values. Okay, question C. This is a hard one. I'll leave it for next week. Okay, the main reason is that I'm not sure myself. So I think, well, I think something, but I'll check. Question D, if you get a linear programming problem, and it turns out that it has more than one optimal solution, okay? Does that mean that the problem must have a bounded feasible region? Okay, who knows what it means to have a bounded feasible region? No one? Oh, no. Who does not know? The rest of you don't know if they know. Fair enough. Okay, a bounded feasible region is, in the case of two variables, what we always used to draw like this, so you cannot have array that would go out of the feasible region and never stop. Okay? Whereas this is bounded. Whereas an unbounded feasible region is one where look like this. So you can take half line that goes to infinity and never leaves the feasible region. This is called unbounded. So the question asks you, if there are more than one optimal solution, does that mean that the problem has to be as in the top picture? Yes, not like this. Okay, so who thinks it's true? It's always like that. Who thinks it's false? It could be otherwise. Amy, what do you think? Both. Oh, false. Okay, sorry, I didn't hear you properly. False. Okay, is that the authoritative answer? Okay, I'll put it down. Just because you're saying it. You're right, it's false. Because it could happen that, for example, this constraint boundary, all these will be optimal. And it's not necessarily that the problem would have a bounded feasible region. So up there. Okay, any questions about this homework for now? Now you know how many you got right. You can mark it. And, doesn't matter whether you did it at home or here. If you got these answers right, just before I told them, you can write them in there. So the next thing we're going to do Okay, I know we've seen the chess set problem before. But before we get on with it, has everybody got the handout today with the chess set problem and everything today? Quite a lot. Does anybody need copies? Good. Right, what did we do with this question? Well, first of all, we turned it into a linear programming formulation. So you don't have to read this all because you've seen it many times before. But what it led to was, I've lost it. What it led to was this formulation, wasn't it? So we had two decision variables, an objective, three functional constraints, and two non-negativity constraints written like this in the mathematical formulation. Then what we did with the problem was we solved it using the simplex method. Okay? And God, that was a lot of work. I mean, for a simple problem like this with two variables and three constraints and pivoting like crazy and a million calculations, and would you like to do that again? Is there a different way of actually learning what the result is. It's this. Now you don't have to copy it because it's somewhere on page 42 of that thing. Okay, it doesn't have 42 pages, but numbering is good. So now I forget what I wanted to say about it. First of all, what is this? Okay, I have a question. Is this MATLAB? No, it doesn't look like MATLAB. Is this any other programming language you know? Okay, for example, who knows C? Is this C? No, it doesn't look like C. Is this Pascal? Is this Python? Okay, any other guesses? Do you know any other programming languages? That it's not. No. Okay, so who knows at least 2 programming languages, just to know where we are? Like knows that there are. Don't have to be able to do any programming in them. But, okay, that's a good start. So this is another programming language, and we shall learn it. And this programming language is called Mosel. And it's programming and modeling language, really, because it allows you to build linear programming and other mathematical programming optimization models. It's quite nice about it. And it has quite a powerful language when you're doing optimization. But what we want to do is to learn the basics today and then tomorrow and so on. Because it's fun. So I can't remember what I wanted to say about it. Well, I probably have to. Well, I do remember, but I don't have the notes. So I'm sure. Surely I will forget something. But it doesn't matter. So let's have a look at it. So this is a simple program in Mosel, and it solves the chess set problem. Okay? And I just want to make some comments about it because, of course, you don't have it in front of you, so it's kind of hard to do something. But in the labs this week and next week and until the end of term, you'll have enough opportunities to experiment with it. You can also download it if you want. There's a link somewhere in the handout and on Moodle as well. And yeah, I just want to show really some very simple basic things. So the program always starts with model because it thinks that every program is a model. And it ends with end model. Okay, so this is always there. That's simple. Now this green bit is not necessarily there all the time, but it practically always is there because if you don't put it there, you can do many things, but you can't solve linear programs. So if you want to be able to optimize things, you have to put this line there. Don't ask me what MMXPRS means. Okay, you can ask me. Anybody want to know what MMXPRS means? Okay, it means Mosel Module Express. It's not an exam question, you don't have to know. Okay. The good thing is you don't even need to remember MMXPRS because when you, yes, just a second, because when you start a new file in the IVE, it has the line already in it. So you don't really need to remember, yes. Express Optimizer, yes. So yeah, so we'll be using this Mosel language with the Express Optimizer. Where do you know it from? Oh, I told him 3 weeks ago. You see, that should never tell students anything because then they use it against them. Yeah, so it is about the Express Optimizer. So it means that we'll use the Express Optimizer. Now, okay, the next important thing, so this is this keyword uses. Then there's this thing, which is called a declarations block. So for the moment, let's just think that in this declarations block, we'll say what decision variables we have. Okay, so when we say that we have, so in our case, you see we have two decision variables. We call them x1 and x2. You can still call them x1 and x2 if you like. But there is this kind of clash between mathematicians and operational researchers. Kind of. Okay, so who's a mathematician? Okay, who's an operational researcher? So, so this, the clash is that mathematicians like things short and concise and very kind of efficiently written. Okay, so they won't bother with anything more than like x, one letter with maybe one index. Quite common for mathematicians to write things in this very compressed form, as it were. Whereas operational researchers and in particular computer programmers, they just like to call their things in the computer code longer names that make sense because they want to understand the things when they read them. And it's quite hard to understand computer code when you read it. And it's completely impossible if the names of the things that you're using don't make sense. So if you were using, if instead of small you wrote this, and instead of large you could use this name. Okay, the computer wouldn't mind. The computer would process everything and it would be extremely happy. But any human trying to decipher the code that you wrote and trying to make out what you meant by it and what it's meant to do would necessarily want to kill you. Okay, so it's good practice in computer programming to use names that have some meaning, like small and large, for example. And okay, now there's this strange word NP-var, and that just means that it's a decision variable. Okay, so small colon NP-var means small is a decision variable. Large colon NP-var means large is a decision variable. Does anybody want to know what NP-var stands for? Okay, MP is mathematical programming.
Number draw is the
So these things are done in the declarations block. So, right, okay. And then the rest looks sort of clear. So you say, define the objective and constraints. Any questions about how they're defined? You look at it. Okay, the questions will only come up when you struggle to write into slides. That seems clear, yeah?
When you apply limits for the variable, like, and you can't start the number,
Yeah, I think they have to be, you have to start with a letter, I think. You can't start with a number. But numbers, the digits can be parts of the names. These are relative details. One important thing is when we're talking about names of variables, one important thing is that it's what's called case sensitive. So, does anybody know what that means? Yeah. So you have to distinguish upper and lower case. And if you write profit with a capital R, capital T somewhere, and somewhere else you write profit like this, and somewhere else you write profit with a capital R. Okay, they're all different names for Mosel. So when you start mixing them up in your code, there will be errors. Be careful about that. It's also a very bad idea to use all three names each for something else. Then you have no idea which one is which. Okay, and answers the question. So after you've defined your objective, so it has to come below all the constraints, you actually run the simplex method inside. Okay, and then you can output the solution. And that's the basic structure of solving a simple problem like this one. Okay, it's all very distant, perhaps, because you don't have the computer in front of you. But even so, are there any more questions about how to write this code? Yes? Oh, that's just later. I could take them out. Okay, so the question is, what's the weird space things? These weird space things are spaces within strings of letters. Well, it's kind of. I mean, it's not that important, but it is somehow important because if you write make and then the double quotation quote immediately after the e without a space, then in the output you won't see a space between the number of small sets and the word make, so it'll look ugly. Okay. So you want a space in the output. You don't want make 16 as one word. You want make space 16. So that's why you need the space here and the space there and the space there and so on. So that's why they're marked there. Okay, any more questions? That would be exciting to learn. Who's excited? Don't get overexcited, man. What else? Oh, I've got some questions. Where are the non-negativity constraints? Yes? It does them automatically. Okay. What if you don't want them? Where's my laptop? I'll just put it as a note. You know, you have it in the handout. Non-negativity constraints. If you don't want them, there is a way to tell Mosel not to put them in, which we won't do now because now we want them. But in due time, we'll see the way. Oh, what are these exclamation marks here? All over the place. Yes, they're comments. Is comment a good thing in a computer code, or is it a bad thing in a computer code? It's a good thing as long as it's sensible. The stupid comment, and it's not a good thing. But that much you probably expected. So in Mosel, the exclamation mark is the start of a comment, and everything until the end of the line is a comment. Okay? So when you're a very common use of the exclamation mark, at least for me, is when something doesn't work in my code, I just put an exclamation mark so that it's ignored, and I do something with the rest, and then I fix it, and then I remove the exclamation mark. So many students have the tendency to just delete everything and then write it again, but it's better to just comment it out, and then you can put it easily back in. It's a general kind of observation. Now, what's the time? Is it time for a break? Maybe. Okay, so this is so much for Mosel. We still have an hour or so. So what we're going to do in that hour is look at some more problems that look like the chess set problem. Got two more in the slide, and we'll write. Because, okay, why are we doing this? Well, we'll write a linear program like this, and the reason we're doing this is because being able to write code like this is great, but you can't write a code like this if you don't know what you want your decision variables to be, and if you don't know what you want your constraints to be, and if you don't know what you want your objective to be, based on some kind of a real-life situation. Okay? And it's quite hard to, I think many students struggle with getting a description like the chess set problem, and then determining or deciding what decision variables are going to be, and what the constraints are going to be, etc. I think the reason students struggle with it is because there's no like set procedure. Okay, so when I give you a problem like this and I tell you to solve it with the simplex method, you just get on with it and you do the table and you do the pivoting and you follow a set procedure. Whereas if I give you a description of a problem, there are machines and there are things going on and there are jobs and there are these things, and there's no like precise algorithm to solve it. Okay? But then that is exactly what you want to learn. Okay? Because doing things by hand that the computer can do immediately, that's not going to get you a job. What's going to get you a job is when you know how to tell the machine what to do, and when you can take a real life problem and put it into the computer and then get the solution. And you have to think while doing it. That's what is important. Okay, let's take a 10-minute break and then we'll get on with the problem.